Part 1. Introduction. Databases serve as the cornerstone of the digital age, providing a structured framework to store, manage, and retrieve vast amounts of information. They are sophisticated systems designed to organize data efficiently, enabling swift access and manipulation. In essence, a database is a curated collection of interconnected data elements stored electronically within a computer system. It's the powerhouse behind nearly every digital application, from social media platforms and e-commerce websites to financial institutions and healthcare systems. The importance of databases in modern technology cannot be overstated. They facilitate the seamless storage and retrieval of information, ensuring data remains organized and readily accessible. Databases are pivotal in maintaining the integrity and accuracy of data, essential for decision-making, analysis, and powering functionalities in various applications. Without databases, managing and accessing the colossal volumes of information generated daily would be an arduous task. Their role extends beyond mere data storage. They provide the foundation for applications to deliver services, process transactions, and adapt to ever-evolving user demands. From structured query language aka SQL, databases like MySQL and Oracle to NoSQL alternatives such as Mongo and Redis, databases come in various forms tailored to different data structures and application needs. Understanding the diverse types and functionalities of databases is key to harnessing their full potential in the digital landscape. As technology continues to advance, databases will evolve, becoming more sophisticated to handle the ever-increasing volumes of data and the complexities of modern applications. Embracing and understanding databases is crucial in navigating the data-centric world we live in today. Part 2. Types of databases. A. Relational databases. Relational databases organize data into tables, following a structured format. They excel in handling structured data with well-defined relationships between various elements. Each table consists of rows and columns, where columns represent specific attributes, and rows contain the actual data entries. These databases enforce the use of a schema that defines the structure of the data, ensuring data integrity and consistency. Examples of widely used relational databases include MySQL, PostgreSQL, and Oracle. Note: relational databases find their niche in scenarios requiring strict data integrity, transactions, and complex queries. B. NoSQL databases. NoSQL databases, unlike relational databases, accommodate unstructured or semi-structured data. They provide a more flexible data model, allowing for scalability and agility in handling large volumes of data. NoSQL databases come in various types, including document-oriented, for example Mongo, key-value stores, for example Redis, and column-oriented, for example Cassandra. These databases cater to modern applications dealing with massive datasets, real-time data processing, and distributed computing. Note: NoSQL databases are well-suited for scenarios demanding high scalability, performance, and the ability to handle diverse data types. C. MySQL databases. MySQL databases combine the advantages of both relational and NoSQL databases. They aim to provide scalability and high performance while ensuring atomicity, consistency, isolation, durability, compliance, which is a hallmark of traditional relational databases. MySQL databases like CockroachDB and Google Spanner are designed for distributed environments, enabling horizontal scaling without compromising on data consistency and transactional capabilities. Note: MySQL databases cater to applications requiring both scalability and strong consistency, making them suitable for modern distributed systems. Understanding the distinctions between these database types is crucial in selecting the most appropriate one based on the specific needs and demands of a particular application or use case. Each type comes with its strengths and weaknesses, allowing developers and businesses to make informed decisions to best serve their data management requirements. Part 3. Database models. A. Relational model. The relational model forms the basis of relational databases, organizing data into tables comprised of rows and columns. Each table has a predefined structure defined by a schema, specifying the data types, relationships, and constraints. Relationships between tables are established using keys, primarily primary keys and foreign keys. Primary keys uniquely identify each record in a table, while foreign keys establish relationships between tables, ensuring data integrity through referential integrity constraints. Note: the relational model's rigid structure is well suited for scenarios demanding structured data with well-defined relationships and complex queries. B. Document model. In contrast to the tabular nature of relational databases, the document model stores data in flexible, semi-structured documents. Documents, often represented in formats like JSON or BSON, contain key-value pairs or nested structures. Collections act as containers for these documents, allowing for a more dynamic schema, where each document can have different fields. Document databases like Mengode offer high flexibility, making them ideal for handling unstructured or semi-structured data commonly found in modern applications. Note: the document model's flexibility is valuable in scenarios where data schemas evolve frequently or when dealing with semi-structured or unstructured data. C. Graph model. The graph model represents data as a network of interconnected nodes and edges, emphasizing relationships between entities. Nodes represent entities, while edges denote the connections between them. Graph databases excel in managing complex relationships and querying intricate networks. They offer efficient traversal of relationships, making them suitable for scenarios involving social networks, recommendation engines, fraud detection, and network analysis. Note: the graph model is highly advantageous for applications requiring analysis of intricate relationships and complex networks. Understanding the nuances of these database models is crucial in selecting the most suitable one based on the specific requirements of an application. Each model offers distinct advantages, enabling developers and businesses to choose the model that aligns best with their data structure and querying needs. Part 4. Importance of databases in business and technology. Databases serve as the backbone of modern business operations and technological advancements. Their significance extends across various domains and industries due to several critical factors. A. Data storage and retrieval. Databases efficiently store and manage vast amounts of data, ensuring quick and reliable retrieval. They enable businesses to organize information systematically, allowing for easy access to crucial data when needed. B. Scalability. The scalability of databases ensures they can handle growing datasets and increased user demand without compromising performance. Scalable databases adapt to accommodate larger volumes of data and user interactions, supporting business growth and innovation. C. Data consistency and integrity. Maintaining data consistency and integrity is vital in databases. They enforce rules and constraints, ensuring that data remains accurate and reliable, preventing inconsistencies or errors in applications that rely on this information. D. Real-life applications. Databases power a myriad of real-world applications. In e-commerce, they manage inventory, transactions, and customer information. Social media platforms rely on databases to handle user-generated content and connections. Financial institutions use databases for secure and accurate record-keeping, ensuring compliance and transactional integrity. Businesses leverage databases to streamline operations, make informed decisions through data analysis, and deliver seamless services to customers. Technology advancements and innovations heavily rely on databases to store, process, and manage data efficiently, forming the foundation of the digital landscape. The role of databases in ensuring data accessibility, reliability, and security is paramount, influencing the efficiency and success of modern businesses and technological advancements. Understanding and harnessing the capabilities of databases is fundamental in driving innovation and addressing the dynamic demands of the digital era. Part 5. Database Management Systems or DBMS. A. Definition of DBMS. A database management system aka DBMS is software designed to manage, manipulate, and interact with databases. It serves as an intermediary between users and the database, providing an interface to perform various operations such as data entry, retrieval, modification, and deletion. B. Functions of DBMS. 1. Data manipulation. DBMS facilitates operations to insert, update, delete, and retrieve data from databases. 2. Data security, it implements security measures to protect sensitive data through access control, encryption, and user authentication. 3. Concurrency control, DBMS manages multiple users accessing the same data concurrently, ensuring data consistency and preventing conflicts. 4. Data integrity, it enforces constraints and rules to maintain the accuracy and consistency of data. 5. Backup and recovery, DBMS provides mechanisms for data backup and recovery in case of system failures or data loss. C. Examples of popular DBMS. 1. MySQL, an open-source relational DBMS widely used for web applications and enterprise-level solutions. 2. Mengode, a NoSQL document-oriented DBMS known for its flexibility and scalability, ideal for handling unstructured data. 3. Oracle, a robust relational DBMS catering to large-scale enterprise applications with advanced features for data management and security. DBMS plays a pivotal role in managing and optimizing database performance, ensuring data integrity, security, and accessibility. The choice of a DBMS depends on the specific requirements and nature of the data and applications it will support. Understanding the functionalities and capabilities of different DBMS aids in making informed decisions when selecting the most suitable system for a particular use case. Part 6. Factors in choosing a database. When selecting a database for a specific application or system, several crucial factors come into play, influencing the choice of the most suitable database system. A. Data structure and complexity. Consider the nature of your data, whether it's structured, semi-structured, or unstructured. Choose a database model, such as relational, document or graph, that aligns with the data structure and complexity of your application. B. Scalability requirements. Evaluate the scalability needs of your system. Determine if the database can handle increasing data volumes and user interactions over time without compromising performance or reliability. C. Consistency in asset properties. For applications requiring strong data consistency in compliance with asset properties or atomicity, consistency, isolation, durability, prioritize databases that ensure transactional integrity and data consistency. D. Use case and application requirements. Understand the specific use case and application requirements. Some databases are better suited for certain applications, such as OLTP or online transaction processing, or OLAP or online analytical processing, while others excel in real-time analytics or handling complex relationships. E. Cost considerations. Evaluate the total cost of ownership aka TCO associated with the database system. Consider factors such as licensing fees, infrastructure costs, maintenance expenses, and scalability costs over the long term. By carefully analyzing these factors, businesses and developers can make informed decisions about selecting the most appropriate database system that aligns with their application needs, performance expectations, and budget constraints. Each factor plays a crucial role in determining the efficiency, reliability, and scalability of the chosen database solution. Part 7. Future trends in databases. The landscape of databases continues to evolve rapidly, driven by technological advancements and changing user needs. Several emerging trends are shaping the future of databases. A. AI and machine learning integration. Databases are increasingly integrating AI and machine learning capabilities. These technologies empower databases to perform advanced analytics, automate decision-making, optimize query performance, and provide predictive insights based on vast amounts of data. B. Blockchain and decentralized databases. Blockchain technology is influencing the development of decentralized databases. These databases leverage blockchain's immutable and distributed ledger capabilities to enhance data security, transparency, and trust in various applications like supply chain management, healthcare, and finance. C. Edge computing and databases. Edge computing, which involves processing data closer to the source rather than relying solely on centralized cloud servers, is impacting database architecture. Databases are adapting to handle distributed data processing, ensuring low latency access, and accommodating the diverse computing resources at the network edge. D. Data privacy and security advancements. With growing concerns about data privacy and security, databases are evolving to incorporate robust encryption techniques, fine-grained access controls, and privacy-preserving technologies. Enhanced security measures aim to protect sensitive data and ensure compliance with stringent data privacy regulations. These future trends indicate a shift towards more intelligent, secure, and decentralized database systems. Integrating advanced technologies like AI, blockchain, and edge computing into databases is poised to revolutionize data management, enabling more efficient processing, enhanced security, and greater adaptability to the evolving needs of businesses and industries. Part 8. Conclusion. Databases are the bedrock of modern technology, playing a pivotal role in organizing, managing, and utilizing vast amounts of data that fuel our digital world. From relational databases providing structured data integrity to NoSQL databases offering flexibility and scalability, each database type serves unique purposes in addressing diverse application needs. The significance of databases extends beyond mere data storage. They empower businesses to make data-driven decisions, facilitate seamless operations across various industries, and underpin the functionality of countless applications we interact with daily. Understanding the diverse types of databases, their underlying models, and the critical role of database management systems aka DBMS, is essential in navigating the complexities of data management and harnessing the full potential of these systems. As technology continues to advance, databases will evolve further, integrating cutting-edge technologies like AI, blockchain, and edge computing. Embracing these advancements will pave the way for smarter, more secure, and highly adaptable database systems, catering to the ever-evolving needs of businesses and individuals in the digital age. In this era where data is paramount, appreciating the intricacies and importance of databases is fundamental in driving innovation, enabling informed decision-making, and shaping the future of technology. The journey of databases continues to be an exciting and transformative one, propelling us towards a more interconnected, intelligent, and data-centric world.